Welcome back. In this lesson, we are going to discuss two important issues and limitations for the KNN algorithm, which are the search space and the curse of dimensionality. So as we know, KNN relies on pairwise distance between points. So if we use more dimensions in our data, which means more features, then the pairwise distance between points will grow, right? And the neighbors may be so far away that they don't actually have much in common with the test point, right? So if we have 5k nearest neighbors, right? So if we have 5 nearest neighbors and then we have a very, very large space, we have so many features. So if you have a very scattered data and you want to calculate the 5 nearest neighbors, then maybe these 5 nearest neighbors will be very far away, that you don't really have any similarity between the test point and the training points, okay? So in general, the length of the smallest hypercube that contains all k nearest neighbors of a test point is k over n power 1 over d for n samples with dimensionality n. You don't really need to understand this equation or understand from where it came, right? Because there is a lot of mathematics behind this equation, but we need to understand the intuition of this equation. So if the number of dimensions increases linearly, so if we increase the number of dimensions from two features to 4 features, then the number of training samples, right, the number of n must increase exponentially, right? Because here we have exponent, right? So it will increase exponentially. Or we can reduce d. We can reduce the number of dimensions. How we can reduce the number of dimensions? Either by feature selection and feature engineering, or by transforming the data into a lower dimensional space, which we are going to see in the unsupervised learning part of this course, right? We are going to use the principal component analysis or PCA to do this. And we can visually see this as follows, right? So this is the smallest hypercube, right? So we have this cube, and as you can see, this cube is just a representation of your space, okay? And this hypercube, right, the cube inside your space that contains the 10 nearest neighbors of a test point, right, we have L representing the length of the smallest hypercube. Now, if n is 100, I don't really want you to understand all this. What I want you to understand is that using this equation, right, the equation right here, if n is 100, it's a very, very small data set in terms of the number of examples we have. If we have only 2 dimensions, okay, if we come here and just insert here d equal 2, and here we have n equal 100 and k equal 10, if you try to calculate it on your calculator, then you will get L equal 0.1, right? So this equation represents L, right? The length of the smallest hypercube that contains all k nearest neighbor of a test point. Now, if we increased d to be 10, right? So if we increase the number of dimensions to be 10, so we have 10 dimensions, then the length of this hypercube will be 0.63, or 63% of your whole space. So you need to search in 63% of your space, right, which is very, very large, in order to get the 10 nearest neighbors. And if we have 100 dimensions, so your space now is very, very, very large, you need to search inside 95.5% of your whole space to find the 10 nearest neighbors. And if you have 1000 dimensions, then you need to search in the entire space, nearly in the entire space. right? So as we can see, if we increase the number of dimensions, then this hypercube, or the number of data points you need to search in order to find the k nearest neighbors, increases exponentially. Okay, so as d increases, we need almost the entire space to find nearest 10 points. Okay, also, to find the k nearest neighbors, we need to find the distance to all n training examples, right? Where n is 100. So this is brute force search. And this O is the complexity of this algorithm. So the complexity of the algorithm is some standard we use in order to know how much time this algorithm will take, right, on any machine. So it will take n times d, right? In order to find the nearest neighbors, we need to go over d dimensions, and for each dimension, we need to go over the n samples. So as we can see, this is brute force search. So this is the curse of dimensionality and the search space. As we can see, the search space is O of dn, and the curse of dimensionality is basically when we increase the number of dimensions linearly, then the time needed and the search needed to find the k nearest neighbors increases exponentially, not linearly. Okay, so we have some extensions, right? And this is out of the scope for this course, but you can search it yourself. One of them is KD trees. Okay, so if you go to k neighbors classifier inside sklearn, you will find that we have algorithm. And for the algorithm, we have something called KD tree. And this KD tree will help you with the brute force search. So instead of going over dn, it will go over d log n. And this is a huge improvement. Okay. And after that, of course, we fed the data and we use the prediction function and we calculate the accuracy. The accuracy will be the same, right? But if you have a very, very large data set, then using the KD search or any other searching algorithm, right, will make your code run much faster. Okay, so this is the curse of dimensionality and the KNN search space. These are two important issues and limitations for the KNN. Now, in the next lesson, we will see some of the use cases for the KNN in order to understand better why KNN is widely used, although it's very, very simple, very intuitive, and it has some limitations. So let's go to the next lesson.